welcome to ML Done, and in particular, welcome to this lecture. Today we're going to talk about binary classification, but just as a quick recap. So we started this series of lectures with defining maximum likelihood estimation, and we said, we kind of showed that basically how it can relate to defining your error function. And then we talked about supervised learning and maximum likelihood estimation, and we showed that how you can introduce your ground truth into your error function because you'd like to compare the output of your network with the ground truth. So what it is and what it should have been, basically. And by minimizing that distance, you're basically maximizing the likelihood, and by maximizing likelihood, you're basically minimizing your error. And if I'm not mistaken, the last session we talked about, regression and what type of a likelihood, what sort of assumption in terms of its distribution you would need to put into your error function to be able to find the best line that would basically pass through your data points with the minimum error, right? So we said that we would assume a Gaussian distribution, and we said that we are basically asking our network to produce, to spit out the parameters of that Gaussian distribution. And we reached to the conclusion that if you apply maximum likelihood estimation, eventually the type of error function that you're going to end up having would be the famous sum squared error function that you can see that is being prevalently used in the literature whenever you're dealing with regression. So today, as promised, we're gonna open the doors towards classification. And when it comes to classification, the first step is to understand binary classification, where you're dealing with two classes. So let's just compare classification and regression and understand their differences. They're actually quite different problems. With regression, the typical question that you are looking for to answer is how much or how many. For instance, if you want to predict the price of the oil in the next n number of days, say next month or next week, that's a how much question. So given the input, which could be anything, you can just think about the stock market, the political situations, I don't know, like the inflation, all those economical terms that you might be able to encode as a number, as an input. So that would be your input. So given that input, can you predict how much would the price of the oil be in the next n number of days? So that is a regression problem. You'd like to basically predict a number, or sometimes how many. You'd like to figure out the number of cars that you're going to sell in the next, say, 10 days. And so the whole idea is to predict the real valued numbers. However, when it comes to classification, you're usually looking forward to learn about the category of the inputs, right? So given an input, which class should I place that input in? So if you're dealing with a, say, image input, right? And say you have classes, ships, dogs, houses, cars. So given an input image, should it belong to class dogs, class car, class houses, which class, right? And not only you're interested in knowing the category, right? You're also interested in knowing the probability of that input belonging to that class, right? So if you have trained your machine learning algorithm that can tell you what category a certain input belongs to, you're also interested in knowing that how certain your algorithm is, right? So that is very important. So you'd also like to produce a probability for any assignment that your machine learning algorithm might do for you, okay? And usually when it comes to classification, we have two types. It's either a binary classification, where you have only two classes to assign your inputs to, or it's a multi-class classification, where you have more than two, obviously. But in this lecture, we're going to focus on just the binary classification, and we're going to cover multi-class classification in our next lecture. Now, in a binary classification problem, typically, just like any other machine learning algorithm problem, you got your input x, right? So, So you got your input x, right? So that would just get into your black box machine learning algorithm, whatever it is. And what you're going to get in the end is going to be the class label, right? So say you have two classes, say class positive and class negative, right? So when your machine learning algorithm observes this x as a new input, you'd like it to spit out your class label for you, right? Like which class does it belong to in your opinion? And typically what you get from, say, a neural network type of algorithm, what you would get is typically a number, which is basically the probability of this input belonging to either of the classes. So you would get something like, say 0.8 for class positive, and guess what would be the probability of class negative here? So we have just two classes, and the input could either belong to class positive or class negative. So if the machine learning algorithm says that with probability 0.8, which means 80%, the input belongs to class positive, so what is the probability of x belonging to class negative? So that would be 20%, right? Because there are no other possibilities. So you usually, the way it works is that you would just subtract 80% from 1, and that would give you the other part of your input space. That, okay, so if 80% is the chances of x belonging to class positive, the only thing that would remain for the negative class, the only share that it would have, the chances that it would have, would be 20%. So you see, if your machine learning algorithm spits out such numbers, then you would say that, okay, so you're fairly confident that x belongs to class positive. And what is important here is that, remember, during training, we are assuming that we're doing supervised training, which means that we have access to our ground truth, right? So we have the ground truth here, right? And say for this particular class, for this particular x, we know that it actually belongs to class negative. And your machine learning algorithm has made a terrible mistake and is nearly sure that that x belongs to class positive, right? So this is training phase, right? It is bound to screw up. So your algorithm would keep screwing up and up and up until it learns. So every time it makes a decision, it makes an assignment to either of the classes, you would tell it how much it has screwed up by a measure of difference, right? So measure of difference between what it should have said and what it is actually saying. Now, how would you say that? Say this particular input belongs to class negative, right? So you would present your network with the ground truth. And how would you do that? You would say that, okay, so you would use 0 or 1 for your ground truth. So you would say, yeah, it doesn't belong to class positive, but it does belong to class negative. See? You're basically using these two values, 0 and 1, to encode the ground truth into your network, right? And it is quite interesting because then the network will realize that, okay, it has made a big mistake. I mean, if it had said that, okay, with 80% x belongs to class negative and 20% to class positive, it would have done a far better job, but it hasn't, right? So what it does is it measures this difference through some error function that we're going to talk about, right? And that error function would tell you, would tell the network how should it change its dynamics, how should it change the parameters. So the parameters inside of it, and by parameters I mean that, remember, we have in a machine learning algorithm, we have parameters. So if it's a neural network, you have weights, right? So these weights need to be adjusted to accommodate the perfect learning, right? So the weights would get affected based on this distance between your network's prediction, the green numbers, and what it should have been, the red line, which is the ground truth. So this error would be computed, and it would be back propagated through the network to the network again. So that is called, especially in neural networks, it's called back propagation. So you are back propagating the amount by which your network has screwed up. That is called the derivatives, but I'm not going to jump into the details of the actual training process. So remember, this module is just on the birth of error functions, right? So what would happen after actually computing the error and computing the derivatives and doing the back propagation, that is a whole other module, okay? So we're gonna have to dig into the neural network itself, show you the parameters, how they would change, showing you this thing called the chain rule. There will be a whole load of derivatives flying in the space, basically. But it's actually quite, well, in my opinion, it's a quite easy concept, the back propagation. But anyways, that is not our topic. I don't want to digress. So that is the whole story. You would, since you are presenting the network with the ground truth coded as zeros or ones, right? 0 would be to either of the classes, and 1 would be for the other class, right? Then you would like your network to produce a number between 0 and 1, right? So if it produces a number like 1000 for positive class and a minus, I don't know, 1 million to negative class, it doesn't even mean anything to you, right? So if you could bound the output of your network between two values, say 0 and 1, then you have the chance to compare it to your ground truth, which is encoded through using 0 and 1, right? And then remember, so if another x happens, like another input comes in, which is quite similar to this class, to this x that you already had, right? You would like your network to do a better job the next time a similar input comes in, right? So you'd like it to be more, less compared to here. You'd like to say, you'd like it to predict, to be more confident about negative class, right? So you'd like it to predict something around, I don't know, 55, and then you would have 55, 60, 45, yeah. Then you would have 45 here, right? So it's doing a far better job compared to the previous input, right? So at the end of the day, what's happening here is that you would have this output vector, right? So this right here is your output vector, a vector of probabilities. This is what your network spits out. And you have a ground truth vector, which is right here, which is what you're going to present to your network to give it a signal as to how it's doing. At the end of the day, an error function, it takes these two vectors and measures the difference, right? And based on these differences, it would give a feedback through backpropagation to the neural network, and the neural network would adapt its weights or its parameters so that it would do a better job the next time. Okay, so that is the whole story of learning in all its glory in neural network. So An artificial neural network, which is usually abbreviated as ANN, it's kind of a probabilistic approach, right? So it generates the probability of your input belonging to either of the classes. So ANN computes the probability of, say, the positive class, right? And then that is basically how we show that. So the P stands for probability. So probability of xi, so x of I would be the ith input belonging to class 1. So the y of I, which is the output of your network, equal to 1, right? So what is the probability of seeing that, right? And as we said, if your model, if your neural network model is just a linear model, like y equals, like right here, I'm going to read it again. So this is the model. So remember that this model is not bounded at all. So y can take any value. So if x is a vector or whatever it is, it can be multiplied by a certain number of weights, which is the w here in this formula, and then plus some intercept, which is a typical way that you would write down a lines formula. Y is not bounded, right? So a line, so when you draw a line, so if this is x and this is your y, no matter how you define y, if y is gonna represent a line is never bounded. So it can go up to infinity and can go down to infinity, right? So line doesn't strike me as a good model to for your classification, because as I said, you're presenting the network with your ground truth, which is either 0 or 1, right? So because of that, you'd like to bound the output of your network between 0 and 1, so that when you compare your output with the ground truth, it would actually make sense. They would be in the same range, right? So because of that, we need a squasher, and you need something, like some sort of function, some sort of a transformation, that it would take the output of your network, right? Before presenting it to you, it would pass it through this transformation, which would squash whatever the value it has between 0 and 1. And then you can compare it to your ground truth, which is a number, which is either 0 or 1. So this is the whole story here, right? Don't feel intimidated by all the numbers and formulas. It's actually quite simple. I'm going to walk you through it. Right. Imagine you got input, right? So the input is, I'm going to show it as x, right? And say x is a vector, right? So it has different values. So, and that if I want to just put a numeric example here, so x could be, I don't know, 1.10 minus 0.3 goes on. Okay, so here x1 is number 1, x2 is 0.10, x3 is minus 0.3, and so on, right? And since it's not this is not a module on neural networks, I'm not going to dig more into the details of what a neural network or a perceptron mean. So in this particular lecture, we're going to focus on the error function, right? Which is at the end of the story, at the end of this diagram, right? So I'm just going to fast forward through this bit here. So all these x1, x2, and xn, so these are the inputs, right? And you got this one here. It's called the bias unit, which has, and by the way, a bias unit has another story, and we almost always use it in neural network, but again, this is beyond the scope of this module. So the whole story behind this neural network system is that the input comes in, some weights, which are here, some weights will be multiplied by these inputs, right? So W1 will be multiplied by X1 plus W2 multiplied by X2 plus until Wn multiplied by Xn plus and B multiplied by 1, right? So basically, if I want to write down Z for you, so this is Z right here. So Z will equal to W1 X1 plus W2 X2 plus all the way b multiplied by 1, this unit right here, which is b itself, so I'm not going to write it down. Okay, so this is what you would have for z right here. Okay, so z is nothing but a linear combination of the input units. Does that make sense? So remember, now this z, as I said, is some sort of a linear function. It is not bounded. So if you take this z and compare it to 0 or 1, which would be your ground truth, which would tell you whether input belongs to class 1 or class 0, it doesn't make sense, because you need it to be bounded, bounded, and not just bounded between any two numbers. You need it to be bounded between 0 and 1, right? So then you can say that, okay, you need it to be, say, 1, but you're 0.6. So you need to increase yourself. Or you're 0.8, but you need it to be 0. So you need to reduce yourself, right? So because of that, because of the fact that you're presenting the network with its values 0 and 1, you'd like to make the z limited between 0 and 1. And that is when this sigmoid function, or what I like to call it, is the squasher, comes along, right? This guy right here. This guy right here, right? So you can see the x-axis on this plot, right? So it ranges from -infinity to +infinity, right? So I just put a simple snapshot of the middle section here, right? And pay attention to the vertical axis. That is of utmost importance. So the vertical axis starts from 0, so the minimum that you will get is 0, and the maximum is 1, right? So whatever x you would consider here, say x is 4, right? If you go up and say the equivalent number here, it's kind of close to 1, right? And if you consider 6 here, it's even, the equivalent value would be even closer to 1. If you consider 2, the equivalent value would be less than 1. If it's 0, if the input to the sigmoid function is 0, the output of the sigmoid function would be exactly 0.5, and so on. If it's negative, it will go all the way towards 0. But the point is, it never falls out of this bound. That is the whole point, right? So the whole point of having the sigmoid function is to squash whatever z could be between 0 and 1, right? And that is called the sigmoid function, or squasher. And as you can see here, this is how we show the sigmoid function. So this is the symbol kind of similar to sigma, small sigma. So sigma of z, that is how we show that. So z would be this guy right here, right? The linear combination of your inputs. By the way, this is a typical thing that you would see in neural networks. So you would have a linear combination of the input, and you would pass it through a transformation. And in this case, this transformation is sigmoid, because it does what we are looking for. It squashes z between 0 and 1, right? And this is how it does it, actually. So z is right here, right? So basically 1 over 1 plus the exponential of, so e to the power minus z, what it does is, it says, I don't care how big or how small z is. I'm going to squash it between 0 and 1, right? So the output is between 0 and 1 in this range. And then whatever it is, you would compare it to the ground truth, right? So if your output is, say, 0.8, say you're predicting the probability of x belonging to class positive, right? And say the output of your network is 0.8, means that with probability 0.8, that means 80%, I'm sure that this input belongs to class positive, right? And say the ground truth that you're going to present to the network is 1, right? So it means that you're only, like, how far are these two from each other? You're nearly 20% away from what you should have been, right? Or the worst case is that if the ground truth was 0, so the differences between these two is huge. It means that you're far away from what you should have predicted, right? So then the network has to adjust itself in a way that it would adjust the output basically towards the ground truth, make it as similar as possible to the ground truth. So as you can see here, depending on the ground truth, whether t sub I is 1 or whether it's 0, it would make a comparison between its prediction, which is this value between 0 and 1, your y basically. So y, remember, it is between 0 and 1, okay? It would compare this value to your ground truth, which is either 0 or 1. And then it would compute the error, which means that how far am I from the ground truth, right? And then based on some magic that is called backpropagation, it basically let the whole network, this section right here, this section is the network, let the whole network know how much it needs to change the parameters, which are the weights here, W1, W2 until Wn and B. How much should it increase or decrease each one of them to make the network do a better job at predicting, okay? So that is the whole story behind binary classification. We get an input, we take the linear combination of all the parts of the input, we pass it through a sigmoid function to squash it between 0 and 1, and then we would compare it to the ground truth, which is either 0 or 1. We compute the differences between the two as a sign of how well we have predicted, and then we backpropagate these information, which means that difference, towards the network, and the network will adjust its weights in a way that it can do a better job for the next input. Okay, so we'll go through our inputs over and over and over. So we have this training data, this huge training data has its ground truth next to itself. Okay, so we will pass through this training set over and over, and we would present the network with the ground truth after every prediction, and then we would let it know how well it's doing, right? So what we're expecting to see here is to see the error that we're going to compute right here, and we're gonna tell you right in a second how you're going to compute it. We would like this error to reduce, right? So that is what we call convergence. So if your error during training goes down and down as you do more and more repetitions, it kind of shows you that, okay, the convergence is happening. Now, it doesn't tell you whether you're doing your training absolutely mistake-free, mind you. Okay, that is very important. Sometimes you can see that the error is going down. Yeah, life is good, everybody's happy, but it doesn't necessarily mean that you're doing everything right, by the way. For those of you who are more expert in machine learning and doing your experiments, make sure that you will go through your code line by line until you figure out you're absolutely sure that it's mistake-free, okay? So just don't take convergence as a sign of being mistake-free, okay? So by convergence, what I mean is you would have typically something like this. So you would have, say, two axes like this. By the way, I cleaned the whole slide to make it more, well, less messy. Yeah, so on the horizontal axis you would have the number of repetitions. I'm going to put rep here, and on the vertical axis you would have your error. Okay, so typically you would see something like this. As the repetition goes on, it can oscillate, but generally it goes down. Okay, something like this. And then, so this is again another module, but for those of you who are a little bit more into this sort of stuff, that is when you have to decide when you should stop training. Remember that having a zero training error is horrible. That is called overfitting. So you don't want to underfit, you don't want to overfit, you want to have a good fit. So that was just a bonus point for those of you who are a little bit more well aware of these concepts. But for the other students, who are actually the majority of my class, hopefully, who are kind of new to this sort of stuff, you don't need to worry about overfitting, underfitting, and that sort of stuff. All I want you to take from this slide is that your neural network would spit out a number between 0 and 1, and you can consider that, you can interpret that as a probability of x belonging to one of the classes, whatever it is, okay? And then, so if it spits out a number, say 0.8, for one particular class, then you would automatically know that the probability of your input belonging to the other class is simply 0.2, okay? Because as a rule of probability, all the probabilities have to sum to 1, okay? Okay, cool. Right, so binary classification, and now we're going to focus on the likelihood and how we can use MLE to reach to the actual error function that we can use for a binary classification scenario. Now, as a reminder, the likelihood, or sorry, the error that we were going to compute, we said that, we kind of showed actually that error, E, equals minus the log of the likelihood. And the likelihood was nothing but probability of T given D and W. D being your input and W being the parameters. Sometimes they show the inputs with, they denote it with D, sometimes with X. So please consider that interchangeable, okay? So anyways, that is the whole idea. So previously for regression, we assumed a Gaussian distribution on this whole likelihood, and we took the log and we reached to the SSE, or the sum square function, right? Now, here, so the output of your artificial neural network is a probability, right? Because you're going to pass it through the sigmoid function, and it's going to be a number between 0 and 1, which is the case with a probability. So let's say that if for a given input xi, right? So x of I here, if that is the input to your neural network, right? And then the vice of I is the probability of that input belonging to the positive class, which means that the ground truth would be, with the t's of I, would be 1. Okay, so we're going to denote the positive class with digit 1, okay, or with ground truth 1. Naturally, if your machine thinks that x of I belongs to the positive class with probability y sub I, if I ask you, then with what probability does it think that it belongs to the other class? All you have to do is subtract y sub I from 1 to get the remaining probability, which is the probability of x of I, or your input, belonging to the negative class, for which you have the corresponding ground truth value of 0. So t sub I equals 0. Okay? So it kind of seems to me that you have two options here, right? So the probability of t sub I conditioned over d sub I and the w, or the parameters of your neural network. Right? So what does it really mean? Let me just recap one more time. So what does this whole thing mean again? So you can ask something like this. So what is the probability, okay, of the ground truth for the ith input be equal to 1, meaning that the input belonging to the positive class, given that you have that input, you can also d sub I, you can show it with x sub I, doesn't matter, and the current, remember, current parameters of your neural network. How probable is this? Okay, so that is the likelihood. How likelihood is it for me to see the actual ground truth appearing at the end of your, as the output of my neural network? I mean, that would be just fantastic, right? I mean, if d sub I, which is your input, actually belonged to the positive class, how great it would be for you to actually get a number very, very close to 1, right? Because that is the ground truth. That is what you want to get, okay? So that basically means how likely, so that's likelihood, isn't it? How likely is it for me to see the ground truth, okay? So let me erase this, make it more clean, right? Lovely. So it kind of seems to me that based on what we said right here, so if the ground truth equals to 1, right? Then you would say that, okay, so y sub I would be the probability, right? That the input belongs to the positive class, right? And for the ground truth equals 0, 1 minus y sub I would show you the probability that your machine thinks that your input belongs to the negative class. So let me repeat it again. So y sub I is the probability that your machine thinks x sub I belongs to the positive class, hence t sub I equals 1. Otherwise, if you want to find the probability of the negative class, you would just say 1 minus y sub I. That is the probability that your machine thinks your input belongs to the negative class, for which you would have the ground truth of 0. So if you want to encode this as a closed form, nice mathematical formula, you would get this right here, right? That is called the Bernoulli distribution. And why is that? Let me just plug it in. So if t sub I were to be 0, okay, what does it mean? It means that this section right here, whatever number y sub I is, if you raise it to power 0, it will just cancel out because it will equal to 1, right? So all you're gonna have to compute is the second section. So probability of t sub I given d sub I and w will equal to only 1 minus the prediction of your network to the power of 1 minus 0, which is 1. So you don't even need to write it, right? So that is the likelihood right there, right? So if the output, if the ground truth for your network, for the input is 0, then 1 minus the prediction of your network is going to show the probability of your input belonging to the negative class. Okay, so y sub I is not going to be what you're going to look for. 1 minus y sub I is going to denote the probability of input belonging to the negative class. Similarly, if t sub I for this particular input was 1, then it means that the second half would be cancelled, because the power would be 1 minus 1, which would be 0, and whatever number, if you raise it to the power of 0, it will be 1. So all you're going to have to compute this time is going to be the other side of this equation, which is y sub I divided by t sub I, which is 1, so I'm not going to rewrite it. So you see, this whole concept is exactly what I described here, but carefully and beautifully basically encoded to a nice Bernoulli distribution closed formula, right? So this here says that if the ground truth is 1, which means that if my input actually belongs to the positive class, then y sub I would be the probability, the prediction of your network for that input actually belonging to the class, to positive class. Okay, so that is how you find this mapping. So for t sub I, y sub I is important. For t sub I equals 0, 1 minus y sub I would be important. Great, so let's derive the error function. Actually, I'm going to do it on the fly. Hopefully I'm not going to make a mistake. So this is the likelihood of observing t sub I given d sub I and w, right? And we explained what it means, and we also said that it's called the Bernoulli distribution. Now, we know that error, I mean, if we're using maximum likelihood estimation, we know that the error equals minus the log of your likelihood, t given d and w, right? And again, very similar to what we saw in regression. Again, the error is minus the log of. So the likelihood, again, as you remember, we said that since the ground truth labels are independent of each other, right? So t sub 1, t sub 2, t sub 3, they're independent of each other. Then, because of that, if you want to find the likelihood of the whole of all of your ground truths being observed, then you can just equate that to the multiplication of observing each one of the ground truth values individually. So the likelihood of seeing t sub 1 multiplied by the likelihood of observing t sub 2, t sub 3 until the n, t sub n. Okay, so this is again the same story that we talked about in the regression problem, the assumption of independence, the IID random variables, if you will. We talked about this, so I'm not going to spend more time on it, just going to write the whole summary here. So this whole likelihood right here for all of your ground truths can be broken down into, I'm just going to put a bracket here, the multiplication. Say I goes from 1 to n being all the number of your training data, the training samples, which is again the number of your ground truth labels. Multiplication of the individual likelihoods of your ground truth. So with t sub I, so for every t sub I, you're going to have the t sub I, an input vector, an input to your machine learning algorithm, and you're going to have your W, your weights. Okay? And then again, we said that the log can just turn the multiplication into a summation, and we said that, okay, we can just make it look a little bit more pretty. So we said that it can be rewritten as minus a sigma, right? And log would be distributed in the internal terms. The sigma of the log of the individual likelihoods, right? So far, nothing new. We've seen this before. Nothing is new so far. Now, the next step is, previously we assumed for regression, we assumed a Gaussian distribution on the individual likelihood, right? But now we're going to assume the Bernoulli distribution that we talked about before, this one right here. Yeah, so for individual ground truths, we're going to assume this particular likelihood distribution. Okay? Now, if we do that, what we're going to get? So then the error would be equal to, again, what I would like to deliver to you in this series is for you to go through step-by-step mathematical derivation and really understand what's happening here. Okay? So this is the new step of this lecture here. So far nothing's new, but here you would have the log of y sub I to the power t sub I multiplied by minus y sub I to the power 1 minus t sub I. Right. Now, this is going to get, again, a little bit cleaner. I mean, actually a lot cleaner. So I'm going to use a couple of rules here. Now, the log of a multiplication can be rewritten as log of A plus log of B. That's the first rule of logarithm. Okay? The second rule of logarithm is if you have log of A to the power, to some power, right? It's a number, whatever it is. That n can come down as a coefficient, and you would still have the log of A. Okay, but the power is not there anymore. So these are two simple calculus rules that you need to have in your pocket when you're dealing with these derivations. So, okay, erase that. Now, as you can see here, what do we have? Here, this is the first term that is being multiplied, and this is the second term that is being multiplied, right? So we have two major terms that we can separate the two from each other, right? So we can rewrite this as minus the sigma of log. So I'm gonna put maybe a bracket here. Log of y sub I to the power of t sub I. Remember, plus, again, the log of 1 minus y sub I to the power 1 minus t sub I, right? The whole thing in a big bracket, right? I didn't do anything weird here, by the way, okay? This is the same story. So this is my A, this is my B. So log of A multiplied by B is equal to log of A plus log of B. Only in this case, A is not a pretty variable. It's actually y sub I to the power of t sub I. So A and B actually have powers inside of them. Okay, that's the only difference here. Now, the next step. Remember I said that, okay, if in a log you have something to the power of a number or whatever it is, I said that power can just come down and be a coefficient to the whole log term, right? So that is the story here, actually. So you see these two powers, one here and one here, they can both come down to the beginning of the log, right? So if I want to rewrite it again, error would be equal to minus the sigma is still there. T sub I will come down, log of y sub I, plus, now, the other power is 1 minus t sub I, right? Multiplied by the log of 1 minus y sub I. And I goes from 1 to n. Now, this, my friends, this is a very famous error function in machine learning. That is called the binary cross-entropy function. Okay, and now I'm gonna actually tell you what it actually does. Okay, it's actually quite intuitive and very, very interesting, actually. Now, the intuition behind it. Okay, that is very important. I really would like you to really understand the intuition behind it. This is actually quite simple. Remember, the prediction of your neural network is going to be compared to the ground truth, and the distance between them is going to tell you how well you've done the prediction, right? So the more similar they are, the less distance you have between them, the better, right? And remember, as we said in maximum likelihood estimation, we said that the error is equal to minus the log of your likelihood, right? Oops. Given d and o, yeah. What does it mean? It means by maximizing the likelihood of observing the ground truth, I'm minimizing the whole error because of this negative sign right here, right? Let's see how this would translate into this beauty over here. Now, let's say that the ground, so you have an input, right? Say d sub I, right? You have this input, and you know that the ground truth for this input, you know that it's 1. Okay, you know that this input actually belongs to the positive class. But anyways, you're gonna give it to your network, and your network is gonna make a prediction and spit out the prediction. Okay, which would be y sub I because it's a positive class. But anyways, if I just want to encode this into this whole error function, so by encoding I mean this. So the error function, look at this reminder over here, down there. So t sub I is 1, right? What would happen to this whole error function over here? T sub I is 1, so the second term would be eliminated completely. That would be 1 minus 1, 0. It would just zero out the second part of the error function totally, okay? And all you're gonna be left out with is minus t sub I log of y sub I. Y sub I is your prediction, right? And since t sub I is 1, all you're gonna be left out with is minus the log of y of I, right? Now, if t sub I actually belonged to the negative class, what would have happened then? Believe me, it's going to be very interesting. Then the error would be equal to, so look at down there. So this time this first term would be eliminated, would be zeroed out. The second term will survive. So you would see 1 minus t sub I log of 1 minus y sub I, right? And then the first term would be just 1 minus 0, so it would be just 1, so I'm not going to even write it anymore. So the error equals minus, oops, we have, wait a second, we have a minus here. Sorry, I forgot that. So with the minus the log of 1 minus y sub I. Now, my friends, please pay attention. Your neural network is prediction of, is outputting a value, right? It's a value between 0 and 1 because we're going to pass it through that bloody sigmoid function over there, right? That's going to squash it, right? Y sub I is going to be the prediction of your neural network. Now, we want to minimize the error, right? Because we have this minus the log of likelihood. Now, let's see, how would this relate to what we just said? So, if the input belongs to, actually belongs to the positive class, then the network will strive to, what are we trying to do? We're trying to minimize the error, right? How can we minimize this error? How can we minimize that? If we maximize the y, if we maximize it, then the whole error will be minimized, doesn't it? Right? Because that would be minus the log of a bigger and bigger and bigger number. So the whole thing, the log of that y sub I would be a huge number. So when you just multiply it by a minus, it will be a very small number, right? So the network will try to maximize the y sub I. That is very critical. Please pay attention to the way I'm putting the wording here. So when t sub I is 1, your artificial neural network tries, it means it learns, right? It adjusts the weights in a way that tries to maximize the y sub I, which is the probability of observing a positive class, which is the case actually, okay? However, in the other case, if the output is, if the ground truth is 0, actually, like it means that your input actually belongs to the negative class, then you end up with this term over here. So again, if you try to maximize this bit, then it means that you're minimizing the error, right? Similar to the previous argument. But this time, this is very nice. So if t sub I is actually 0, then your artificial neural network tries to maximize 1 minus y sub I, which means 1 minus the prediction. And would you care to tell me how can we maximize 1 minus y sub I? Any idea? Last chance? Come on! This means by minimizing the y sub I. Because if you decrease y sub I, it's only then that 1 minus y sub I would be maximized, right? So basically, in one sense, in one case you try to maximize y sub I, and in one case you're trying to minimize y sub I. which again jives with what we're trying to do. Just get out of all the math that we've talking about. So if the ground truth for your input is either 1 or 0, if the ground truth is 1, you'd like to maximize your output to make it as close as possible to 1. And if the ground truth is 0, you want to minimize your output, which would get as close as possible to 0, right? And what is the output? It's y sub I. You have just one output here, okay? So that was quite important to understand. So that is the intuition behind the binary cross-entropy function. That given a ground truth, you're trying to do different things, opposite things actually, right? So given a positive ground truth, you're trying to maximize your output. Given a negative ground truth, you're trying to minimize the output to be as similar as possible to the ground truth. Then your error would be minimized, right? And that is the whole idea. And how do we minimize or maximize the output? What does it actually mean? That is the whole idea, my friends, behind training an algorithm. Okay, so training means see how much you've screwed up, right? Adjust yourself, adapt. And that is how your neural network will adapt and change the parameters inside of it to make the output as close as possible to the ground truth. Okay? Cool. Okay, great. So the morals of the story. So as you remember in the regression case, the output of your neural network was basically the parameter of that Gaussian distribution, which was the center, the mean, right? It's again the same story here. If you pay attention here, if I just show you one more time, basically, okay, let me go a little bit more back here. Yeah. So the output of your neural network is the parameter of your Bernoulli distribution. So y sub I is, in mathematics, it's called the parameter of this distribution. And that is the output of your neural network, actually. So in that sense, nothing has changed, okay? So after generating the first y, okay, and seeing the ground truth, your artificial neural network tries to adjust the weights in order to minimize the binary cross-entropy function. And we saw that minimizing the binary cross-entropy function has different intuitions here. I mean, not different, but different ideas, basically, what I mean. Like, so for instance, in order to minimize the binary cross-entropy function, if the ground truth was 1, we saw that the network will try to maximize the output as much as possible. And we saw that if the ground truth is 0, the network automatically would try to minimize this. By what? By adjusting the weights, okay? So some of the weights will increase, some of them will decrease, but eventually you will learn to generate the correct output, okay? And for binary classification, we assume that the likelihood, the probability of observing the ground truth given the output of your network, y, is binomially distributed. And then the associated likelihood really looks like the binary cross-entropy error function. Okay, so if you just go out there and ask people in the world of neural network, they might not all know that why we're using binary cross-entropy function when you're dealing with a binary classification problem. But now you know why you do that. Again, so you see the word binomially distributed here. A more correct way of saying that would be Bernoulli distribution. But again, Bernoulli distribution is a special case of binomial distribution. Either case doesn't make a difference here. Okay, you can just look it up, but either case would be right. Bernoulli would be more accurate. Okay, I don't want to jump into the details of that because it's not really relevant to this module here. So yeah, it is again important for you to know how we come up to these derivations and how we come up with these error functions, because there are many cases. If you just go to the papers from the industry, from academia, you actually see that there are many cases where the application requires a new error function, a different type of error function. And you need to know how to derive these basic ones in order to come up with your own to accommodate your needs for that particular application in the industry or in the academia. Whew! Oh my god, that was that was great actually. I hope that you've enjoyed that yourselves. So in this module, in this lecture, we talked about binary cross-entropy function, and we talked about the distribution that you need to assume on the likelihood to basically come up with a proper error function that would accommodate your application here, which is binary classification. So again, the whole idea is, given an input, you'd like to assign a category to it, and basically the number that you generate as the output of your network would basically show the probability of you assigning that input to either of the classes. Okay, so basically by tradition, the way they look at it is that they always assume that you're generating the probability of the positive class. But either way, that's just the standard way of looking at it. But you can also assume that number to be describing the probability of your input belonging to the negative class. Doesn't make a difference really. Binary cross-entropy function would take care of that. Whichever you choose doesn't make a difference. So again, by minimizing your error function, you'll maximize the likelihood of observing the ground truth and minimizing the difference between your output and your ground truth. I hope that this has been informative for you, and I'll see you in the next class, in the next lecture, where we're going to talk about a more general case of classification, which is the multi-class classification. And we're going to tell you how you can come up with an error function that will accommodate that need. So until our next class, on behalf of ML Don, take care of yourselves, and bye.